Okay. So today what I want to do is I want to continue talking about the nearest neighbor problem. The original itinerary was for me to talk about range searching today. But I'm going to make a little bit of a change. I want to talk about nearest neighbor searching again. And I want to talk about more refined techniques for solving this problem. So I'm going to do a little bit of review from the material that I discussed last time in case anybody was not here or maybe have forgotten. So the general topic that I want to talk about is proximity searching. In particular, I want to talk about nearest neighbor searching. So finding the closest point. Given a set of points, I want to pre-process them to find the closest point to a given query point. Assuming low-dimensional vector space, Euclidean metric. I didn't mention this last time, but you know, the area of nearest neighbor searching has many, many different applications to all different areas in engineering and computer science, pattern recognition, object recognition, content-based retrieval, clustering, phylogeny in biological databases, you know, data compression, et cetera, et cetera. And I'm going to talk about a few topics here. I think what I'll probably do is skip this last topic for the interest of time and talk basically about our latest techniques in the area of data structures for nearest neighbor searching. And there's some very interesting results that are sort of generally about approximating shapes, which even if those of you who are not interested in nearest neighbor searching may find these ideas kind of interesting. They're very, very nice ideas about how to approximate shapes in geometric settings. Okay, so as I mentioned before, the assumption is we're going to deal with a d-dimensional space. We're going to be dealing with the Euclidean distance. We're going to have the nearest neighbor searching problem. That is to pre-process the point set so I can find the nearest neighbor. And last time I described the fact that, you know, in practice, it is sufficient to find not the exact nearest neighbor, which would be this point P star, but to find, let's say, an approximate nearest neighbor. So I will give you some error-bound epsilon. You may find any point that you like within that error bound. And also last time we discussed the idea of the AVD, or approximate Voronoi diagram. Remember, the difficulty in doing nearest neighbor searching in high dimensions is twofold. One is that the Voronoi diagram has very high complexity, and the second is that there are not efficient data structures for doing point location, that is, determining which cell contains a point. So to solve this problem, first off, we use a quad tree decomposition. Why? Well, because a quad tree decomposition, we can do point location very efficiently, right? It is just a tree, and we can just descend through the tree. The issue, though, is that while there may be fairly few cells in the Voronoi diagram, there may be many more cells that I need in the quad tree in order to approximate this, right? So in this region, yes, I know this is the nearest point. In this region, I know this is the nearest point. But here, the problem is, you know, because the bisector is here, it could be one of these 2 points. I should refine until I am sort of the size of this cell is about epsilon times the distance here. In that case, even though the bisector goes through, I could either say this or this. I'm approximately correct with either answer. Okay? So Harpeled presented these results, and I talked about these last time. And we also talked about the fact that if instead of storing just one representative nearest neighbor, if I allow you to store, let's say, up to t representative points, and in this case, I'm allowing maybe 2 representatives, that you can actually use a much smaller subdivision, right? Why? Well, again, you know, in this region here, it's not clear. You know, if the query point is here, this is the nearest point. If the query point is here, this is the nearest point. But that's fine. I can store 2 representatives in each region. And I guess in this one example here, this cell here, right, I can store P1 and P2 because I know one of those 2 will be the nearest neighbor for this point. Actually, you'll see there's a very tiny bit up here. For some query points, this might be the nearest neighbor, but the idea is for approximate nearest neighbor searching, P1 and P2 is sufficient. And the idea is by adjusting the value of t, I can achieve a trade-off between space and time, right? So as t gets to be bigger, the query time goes up. And you might say, well, wait, you have fewer cells in the subdivision. Yes, but when I get down to the leaf level, I now have to do a nearest neighbor search against all t representatives. Okay? So the query time will generally depend upon t. As t gets bigger, the query time is more, but I have fewer cells in the subdivision, so the space tends to come down. Okay. And then last time, I kind of tried to draw this picture here. Unfortunately, the printing is going to be very hard for you to read, but let me sort of tell you what the result is. The result says that if you let the storage, and the storage is represented, let me write this out perhaps so it's a little bit easier. Maybe here's a marker. Okay. So the x-axis says my storage space is going to grow as n divided by epsilon raised to the power of, let's say, approximately d times x. Okay? So if I think about this going from 0 to 1, what is happening is, right, this term is going to be going, well, when x is 0, I'm just going to get 1 down here. When x is 1, I'm going to get epsilon to the d, right? And so at one extreme, I just get O of n space. At the other extreme, right, at the two extremes, I get n. And at the other extreme, I'm getting n divided by epsilon to the d. Okay? And then for the y-axis is going to be my query time. And the expression here is going to be essentially, there's going to be a log factor, and then there's going to be 1 over epsilon times y to the, let's say again, y times d roughly, or let's say d times y. Plus or minus a couple constants here. And this is going from essentially 0 to 1/2. Okay? So when y is equal to, or maybe I'll write it this way, from 1/2 to 0. So this is one from 0 going up to 1. This is going from 1/2 down to 0. And so when I have a value of 1/2, I get a running time of roughly epsilon to the d over 2, the query time. And at the other extreme, I'm essentially getting constant query time. But again, there's a log factor here. So it's not really exactly a constant, but it's very close to efficient. Okay? And last time I mentioned that using an AVD, one gets this curve here that demonstrates that you can actually go from, linear space, which is great, but a somewhat higher query time. Okay? At the other extreme, you get a lot of space. Remember, think of, if epsilon is a small number, if d is marginally large, the space is going to be pretty big, but the query time is going to be extremely good, right? And so you can adjust these two things. We also proved, and it's hard to see this curve here, but there's a lower bound that we proved for the AVD model, which shows that at this extreme, that's as good as you can do. And at this extreme, this is as good as you can do. And the problem is in between, we have this gap between what the best time bounds are. Okay? And the question that we have been looking at for a long time is whether we can close the gap. Which is the true answer? Is this correct, or is this one here correct? For a long time, we really thought this was the best answer, and the lower bound was kind of weak. The reason is because, right, this is a very nice curve, right? It's a straight line. Mathematically, straight lines should be the correct answer. And so we worked for a long time on trying to prove that this is the best by improving our lower bound. The weird thing was, at some point in time, we discovered that actually this is not the case. That in fact, the lower bound may actually be the correct answer here. And it's the upper bound that needs to get fixed. And I want to talk about these new results that we had on this particular problem. Okay? So the new results came about from a completely different way of thinking about the problem. From the perspective of what we would call polytope approximation. So I'm going to describe polytope approximation. I'm going to describe sort of a method for doing this, and I'm going to describe how this relates to the nearest neighbor problem. Okay. So first off, what I want to talk about is, well, what does polytope approximation have to do with nearest neighbor searching? And for those of you who've studied maybe a course in computational geometry, will know about this trick of lifting points onto the paraboloid. But if not, I'll describe the idea here. And it's by the way, this is a very nice generic idea. In general, if you have a sort of a nearest neighbor problem you want to solve, and you want to think of it from a different perspective, this reduction gives you a different way of thinking about nearest neighbor problems in terms of concepts like envelopes and hulls and things like that. So let me explain the construction here. Construction works as follows. What I want you to imagine is that your space in which you want to do nearest neighbor searching is this line. So in general, imagine, for example, if I'm doing this in the plane, think of this line here as being the plane itself, a horizontal plane. Okay? And so, for example, P is a point, maybe I want to think of Q as being my query point or something like that. Okay? And suppose they're separated by a distance of delta. Okay. Now, here's the transformation. You consider a paraboloid. Okay? Paraboloid is just the simple, standard thing. So I can think of it as something like this. Y is equal to x squared. Okay? Or more generally, you can think of the dth coordinate as being the summation of the first, I equals 1 through... Actually, the way I want to think of it is this is happening in one dimension higher. So maybe I should think of it this way. If this goes to d plus 1, maybe I'll think of... so I'm transforming points from d-dimensional space into d plus 1 dimensional space. And so one way to write this would be, I'll take the sum of squares of the components, and my last coordinate will be equal to that quantity. And so that'll basically lift the points onto this paraboloid. Okay, so here's an example. I've lifted this point P. And when I have lifted the point, what I'm going to do is I'm going to imagine that P induces a tangent hyperplane at that point. Okay, in 2D this is just a line, but in 3D, right, my paraboloid is this big bowl, infinite bowl, and then when I lift the point up, I'm going to have a tangent plane at this point. Okay? Okay, here's the interesting fact, which is very easy to prove, that suppose I take any point at distance q, the difference between the top and the bottom point, the point on the paraboloid and the point on the hyperplane, will essentially be the square of the distance between those 2 points. Okay, a very simple exercise in basically just algebra to prove this fact. And so here's the idea then. If I want to compute the nearest neighbor among a group of points, okay, what I'll do is I'll lift them all up onto the paraboloid. Step 1. Step 2, I'll construct all the tangent hyperplanes. So for this one, I have this tangent hyperplane. For this one, this tangent hyperplane. For this one, this one. Okay? I compute their intersection. So in 3D and higher, right, I have a bunch of hyperplanes, right? If you remember the intersection of, think of the half spaces that lie above these hyperplanes. Each one of those is a convex set. If I intersect all these half spaces, I get this big convex bowl. But now, rather than being the paraboloid, which is smooth, this will have facets on it, right? It'll be a polytope. Okay? And then the important observation will be this, that what does this have to do with nearest neighbor searching? Well, in nearest neighbor searching, I want to know which of these points is closest to me. Okay? Here's how I do that. I lift that point up and I ask, what facet, right, of this polytope does that, think of this as a vertical ray shooting query. What do you hit? Okay? The facet that you hit actually will correspond to your closest point here. And that's very easy to verify, right? Because if you remember, the distance here is equal to the square of the distance. So that increases monotonically. Essentially, the first guy that I hit will be the one that I'm going to be closest to. Okay. In fact, here's sort of a three-dimensional rendering of this idea here. So here what I've done is I've taken my red points are the points in the plane. I've lifted them up onto my paraboloid. I build these tangent hyperplanes. I intersect these hyperplanes, right? And then I get this kind of infinite convex polytope. And if I have a query point, let's say a query point here, right? I want to know who the nearest neighbor is. I lift that guy up here. I find out which facet I'm in. And the point associated with that facet will be my nearest neighbor. Now, of course, the problem is that polytopes in high dimensions have got very high complexity. I cannot build this structure. It is just going to be too big. Okay? In general, the space will grow as something like, n to the, it's normally n to the floor of d over 2. But if you think about it now, I'm actually doing this in d plus 1 dimensional space. So it's going to really be n to the ceiling of d over 2 is going to be the worst case complexity of that object. So the problem is this is really too big. Right? Too much storage for me to store this whole shape. So what are we going to do? Well, we want to do this approximately. So the way I want to think of this approximately is I want to imagine that suppose someone gives me a polytope of perhaps very high combinatorial complexity, lots and lots of facets. And I want to say approximately is a point inside of that polytope. So how do I think of this? I'm given a polytope P, d-dimensional space. Really, d is going to be d plus 1 when we apply this, but for now, let me just think of it as dimension d. I'm going to be given a point Q, and I want to know, is Q inside that polytope or not? Okay? So, again, I'm going to assume that the polytope is d-dimensional, and it is given as the intersection of half spaces, because that is what my reduction gives me here. And the approximate version of the problem will be stated as follows. I want to know whether Q is approximately in this. How do I do that? Well, I'm going to do it as follows. I'm going to take my polytope. I'm going to assume that it's bounded polytope, and I will reduce its diameter to 1. You might say, hey, wait a minute. You began with this infinite polytope. And what I'm going to do in that case is I'm just going to, put a box around my polytope. So I can always assume that the polytope is going to have some kind of bounded diameter. And then I'm going to take it and then I'm going to shrink it down to normalize it so that its diameter is going to be 1. Okay? And then what I'm going to say is this. If the point lies, let's look at the region consisting of an epsilon inside and outside. So I think of epsilon now as an absolute value. If you're inside, you have to say in. If you're outside the shaded region, you have to say out. But if you're in the middle here, sort of, close to the boundary, you're allowed to give either answer, inside or outside. Okay? So this is what is meant by an approximate polytope membership query. Okay. And the idea will be this, that I want to solve nearest neighbor queries. The way I'm going to do it is I'm going to lift to a paraboloid, right? I'm going to then solve approximate polytope queries, and then I'm going to come back to the original problem. Okay. So let's see, how do we do this? A little bit of technical stuff here. If you remember, the problem is being solved within the context of the approximate Voronoi diagram. And the question is, how do I go from the AVD representation to this polytope representation? So what I'm going to say here is the following. Suppose you imagine, if you think about the AVD, last time I described the AVD, I gave you a very high-level representation of it. But here is perhaps a somewhat more concrete way to think about the AVD. In the AVD, what you do is you subdivide space into a bunch of cells. Okay, so every cell, let me use the black marker here. Every one of these cells is going to be, think of this as being a leaf cell in your AVD. Okay? The way in which we guarantee that you can solve nearest neighbors is by essentially arguing that all the points in the data set will be reasonably far away from this point here. I don't care how many points there are here. There may be many, many points, but I have a certain amount of separation. Okay? So for example, if this side length is, s, this distance here might be some maybe parameter gamma times s, where I'm going to assume that maybe gamma is a parameter greater than or equal to 2, and my trade-off is going to be determined by gamma. As I make gamma bigger and bigger, right, what's going to happen is it's going to essentially force my cells to become smaller and smaller. And this is actually how we achieve the trade-off, is we play around with this parameter gamma. Now, of course, the problem is I can't assume that all the points are going to be far away, because if I have a point, some leaf in my quadtree cell has to be close to it. So in general, there might be one point that's going to be nearby. So one point nearby, all the other points far away. And the idea then is this. This point, okay, fine. I'm just going to handle this guy by sort of brute force. Because, when I compute my nearest neighbor, remember I have t representative points. This will be one of my representative points. Okay? So this guy I can sort of ignore. He's taken care of. How about these guys out here? Well, again, I want to think of the paraboloid example. In the paraboloid, what's going to happen is, right, these points that lie outside here, right, are going to be sort of lifted up onto my paraboloid surface. Okay? And then they're going to form this polytope here. The polytope has this, so what's going to happen now is and by the way, the number of points that I have here could be extremely large. Okay, there's no limit on the number. So there's lots of points. Therefore, the polytope that I get here could also be extremely large. I'm going to approximate this polytope, and by approximating the polytope, the claim is what will happen is now I'll approximate the nearest neighbor here. Okay, this is the idea. So we're going to use this lifting transformation to transform from a nearest neighbor, basically from a polytope problem to a nearest neighbor problem. Okay, and now I'm going to describe to you a very nice idea. If you've never seen this, this is the best idea to remember from this talk. The question is, if I give you a polytope which is very complicated, how do you represent it using a small number of facets? And this approximation was actually discovered by two different people. Dudley was one, and I guess the other group was a group from Russia. Bronstein and Ivanov were the pair. And they were very, very close to one another. I believe that Dudley's construction was like in 1974. Bronstein and Ivanov may have been like a year earlier in 1973. But yes, but because they were in Russia and it was not as easy to, this was before the, when things were relatively closed, this was the Soviet Union, right, not Russia. And so it was very difficult for them to disseminate their information. So although they had solved the problem, people didn't know about the solution. Dudley solved essentially the same problem. But nonetheless, I think both of them are given credit for the idea. So here's the question. Suppose I give you a polytope here, and I want to imagine this polytope has a huge number of sides, right? In general, when you go to polytopes in higher dimensional space, you will get lots and lots of facets. This is just, this is the fact. So the question is, how do I come up with a simpler representation of that? And your intuition would be, well, what I should do is I should sample points around the boundary here. Okay, but how do you do the sampling is the question. In particular, if the polytope, is nice and flat, okay, I can sample points, fairly sparsely. But if the polytope makes a sharp turn, I must sample points more densely, right, along this region. And the question is, how do I define sort of a reasonable algorithm for determining how I should sample points in order to get a good approximation? So Dudley suggested the following very simple idea, and Bronstein and Ivanov had exactly the same idea. Here's what you do. You take your polytope, you basically enclose it in a sphere that's about twice as large. Okay? Any constant factor expansion would work. On the sphere, you then sample points where the angular distance on the sphere is going to be about square root of epsilon. Okay? You want to get an epsilon approximation. So in other words, I want it to be the case that when I build, let's say, my bounding hyperplanes here, that the error that I'm going to have here is going to be about epsilon. Okay, so how do I do that? I sample points in this particular manner on the sphere, okay? And then what I do is for every point, I compute its nearest neighbor on the boundary. So I just project that guy till I find its closest point on the boundary. And notice the phenomenon here. If I have a very flat side, then I'm going to get a small number of points that will come there. On the other hand, if I have a very, very sharp pointed angle, right, then a lot of points will come to that particular area. And so what Dudley showed is that if you do so, you can approximate the polytope using the following number, epsilon to the d minus 1 divided by 2. Well, let's think about that. Y divided by 2, well, if you think about it, everything here, remember, this has unit diameter. So this thing has a constant diameter. So the total area of the sphere is going to be a constant. Okay? I'm sampling essentially at a distance of 1 over square root of epsilon. I can do that, by the way, in any dimension. So if I think about, if I have this amount of distance, and if I have a constant amount of sort of surface area there, the number of points that I'm going to need is going to be like 1 over square root of epsilon, right? In general, it's going to be a constant, right? Because that's going to represent your perimeter. But let's just call it 1 over square root of epsilon raised to the power of d minus 1. Why? Well, because this is a surface of dimension d minus 1, right? The entire dimension is d, so the surface of the sphere is d minus 1. And so that's just going to be the same as 1 over epsilon to the d minus 1 divided by 2. Okay? And by the way, you see the number d minus 1 divided by 2 appearing in my talk. It'll always be for this particular reason. It comes from this construction of Dudley. Okay? So here's the idea. Now I have an algorithm that will allow me to answer approximate polytope queries. And I do it as follows. I run the Dudley construction. Okay? That gives me a storage of 1 over epsilon to the d minus 1 over 2 if I just store all the half-planes. Then when I want to answer a query, I just do brute force. I just check every one of these half-planes. I say, you know, here's a half-plane. Is Q inside of this half-plane? If it is, you know, well, okay, I keep trying it. Is Q inside of this one? Is Q inside of this one? If Q is ever outside of a half-plane, then I just say out right away. If, on the other hand, if every answer is in, right, then the answer is it's definitely in. And, of course, I could make a mistake here, right? If Q is in the gap between two of these guys, and I guess I show a picture here. So if Q is in a little gap like this, well, then I'll make a mistake, but the mistake is going to be very small. Okay? By the way, the mysterious thing about this might be the question, why did you use square root of epsilon and not just epsilon itself, right? And this is actually the really clever part of Dudley's construction. I'll just mention very briefly without giving a complete proof. But what Dudley shows is something like this. This is why the value is sort of the right value to use. The argument that he makes goes something as follows. He says, suppose you have, let's see, something like this. If you have a point on your polytope, here is your polygon P, I guess. Let's say I have a point Q. If I look at one of these sampled points out here, what do I know? Well, let's find Q's closest point on the outside here. I know that there will be a sample point whose distance is going to be less than or equal to square root of epsilon. Okay? So again, Q is an arbitrary point. P is going to be one of my sample points. Maybe call this P prime. This is going to be a sample point by the Dudley construction. If I compute P's nearest neighbor, well, the first argument is this point can be no further away, only square root of epsilon. Okay? But remember, epsilon is smaller than 1. So square root of epsilon is actually bigger than epsilon, right? It's not smaller than epsilon, it's bigger. But still, this is not too big. And then the other thing that's observed is the following. That if you look at the angle between this vector and this vector, okay, let me just look at this angle here. This angle theta is also going to be less than or equal to square root of epsilon. And that comes about because of the sampling, right? The sampling is done at angles of epsilon. So I know that there's going to be a point such that the distance is going to be less than or equal to root epsilon. The angle is going to be a bit less than a root epsilon. And when I look at the plane that's coming out here, right, you kind of look at this triangle. This angle and this angle are going to be the same. Okay? If I have a triangle where the base is less than or equal to square root of epsilon, and if I have a side where the angle is going to be less than or equal to square root of epsilon, right, then it follows that the error that I'm going to have here is going to be less than or equal to up to constant factors root epsilon times root epsilon, and that's going to give me an epsilon. Okay? And so this is how Dudley's construction works. It's using the fact that both the distances and the angles are going to be well approximated. Therefore, I'm going to get a value of roughly epsilon here. Again, a very nice construction. Right? You can go to sleep for the rest of the talk. This is the one thing that you should remember. Okay. And so this is the final polytope I get, is the intersection of these half spaces here. Okay. So this leads to a very simple idea for how to achieve a trade-off. The problem with Dudley's algorithm is there is no trade-off, right? You always have the same storage bound. So can I somehow trade off space and query time? So here was an idea that we came up with. It's a very simple idea. What we're going to do is, again, remember that your polytope has unit diameter, diameter 1, so we can put it into a big square of constant size. Okay? You get to pick a value of r between epsilon and 1, and the trade-off will be determined by what value of r you pick. So if you want bigger query time, you make r bigger. If you want smaller query time, you make r smaller. Okay? And then here's what you do. You build a grid. Okay? You basically then look at the intersection of each one of these cells that intersects, let's say the boundary, if it intersects a cell, I'm going to run the Dudley construction just within that cell alone. Okay? So apply Dudley for every one of these cells Q. So let's think of this guy perhaps as a cell. I'm going to apply Dudley to just this polytope inside of here. And, well, think about what the error is going to be. Remember that the way Dudley works is it assumes that the object that you're given is going to have diameter 1, okay, and it wants to produce an error of epsilon. In this case, the diameter is much smaller. The diameter is going to be proportional to r, so it's less than 1. So I can deal with a smaller error as well, right? The error now is going to be not epsilon, but it's actually going to be r times epsilon. And so when I actually I guess the way you could think about this is if you take this guy and sort of scale him back to the case of Dudley of diameter 1, right? What will happen as a result is the error that I'm allowed is going to be changing from epsilon to, well, epsilon divided by r. Okay? So as a consequence, this is the amount of storage that I'm going to have per cell after the scaling trick. Okay? And because r is less than 1, right, this is actually going to be smaller. So the idea is as I make r smaller and smaller, I'm going to get fewer and fewer half spaces per each one of my cells. Oops. Okay. So the query processing now works as follows. Very simple algorithm, right? I just have a grid. I don't even have a tree. Query point comes along. I find the cell that contains the query point, right? I check to see whether Q lies within every half space of this query thing. How many half spaces do I need to check? The answer is you only need to check this number here. Okay? And what is this number? Well, again, if r is 1, it's the same as Dudley. But if r is epsilon, right, I get epsilon over epsilon. I only have a constant number that I have to search. So again, the two extremes will look something like this. At one extreme, right, so by the way, this is going to be low space, high query time. I have just one block, and I'm going to have, right, Dudley's solution here. Okay, so I get the low space in this particular case is just going to be a constant. The query time in this case is going to be 1 over epsilon to the d minus 1 over 2. Okay, at the other extreme, what happens is the grid now is broken up into lots and lots of tiny little pieces. Each piece here is going to be of size about epsilon. Okay. Within each one of these pieces, I only need one approximating half space. So here, the space is going to be potentially much larger because I have to store lots and lots of cells for each one of these cells that overlaps. So the space is going to grow up to essentially 1 over epsilon to the d minus 1. Okay. On the other hand, the query time is going to be very fast. The query time is just going to be a constant because I have one plane here. Okay. And blah, 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 blah. So do I have the final result? So the final result looks something like this. That you wind up getting a storage time that grows as 1 over r times epsilon to the d minus 1 over 2. Okay? And you wind up with a query time, which is r over epsilon to the d minus 1 over 2. Okay? And let me just see if I got them both right. Blah, 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 blah. So... right. So when r is equal to, I wanted to look at this particular case. When r is equal to epsilon, my storage turns out to be, right, it's epsilon times epsilon to the d minus 1 over 2. So that's basically epsilon to the d minus 1. So I get this result here where I have 1 over epsilon to the d minus 1. Query time is going to be a constant in that case. Okay? So you get this nice little space-time trade-off, a very, very simple data structure. Okay? All you have to do is to be able to run Dudley on each one of these guys. Okay. Very nice. If I rephrase this in the form that I was using earlier, right, r is kind of a geometric value, but I can kind of use a change of parameters and describe r in terms of a parameter alpha. And this relates my results, I guess, to the earlier results that I had described. Going back to some of the earlier slides, right, I described the running time of the, let me see, where was it? Yeah, here. I described running times in terms of this parameter alpha. So we get 1 over epsilon to the d over alpha, n over epsilon to the 1 minus 2 alpha, blah, blah, blah. So coming forward, right, I can express the bounds in sort of in a similar manner to what we had before. The difference is, I guess, there's actually a factor 2 over here instead. But very similar way of stating the result. This is already kind of nice, but in fact, what do I want to say about this? Yes. This actually already gives us an improvement over the bounds that were described before. But I want to go a little bit further, and I want to describe this kind of how one takes this idea and pushes it a level farther. So the idea goes something like this. If you look at the Dudley algorithm, I mentioned the good thing about Dudley is if you have places where curvature is high, it samples a lot of points there. If you have places where the curvature is low, well, then it doesn't sample very many points at all. But nonetheless, it actually, if you analyze it, it actually is doing a little bit too much sampling in places where the curvature is very high or very low. Okay, so this is really a problem with Dudley. And we kind of recognize that this seems to be the place where, where the algorithm is not doing the best that it possibly can. So this raises the question of, can I actually do better by trying to be a little bit smarter than doing what the Dudley approximation does? There were algorithms that were based upon sort of efficient approximations by other people. Our idea was we wanted to define a sampling process that is sort of sensitive, right? The grid-based algorithm was just very simple. You just put a grid on things and you sample within each grid. But that doesn't take into account the fact that some regions of the grid cell have very high curvature. Some grid cells maybe have very low curvature. Can I do better? This was the question that we asked. And so this is what gave rise to our notion. It's sort of a hierarchical version of the grid algorithm, which we call split reduce. And here's how it works. Okay, again, this is a very simple algorithm. What I'm going to do is I'm going to input the polytope, epsilon, and whatever the query time is that I desire. And again, query time, we're doing a space-time trade-off. So the user is going to tell us kind of, well, how much query time do we want? And we're going to figure out the best space for that query time. Okay. Let's begin by assuming that we'll start with the unit hypercube. I'm going to assume that everything fits in the unit hypercube, and then I'm going to call split reduce on this function. And here's what we do. There's a quad tree, okay? We split the quad tree into pieces, and we ask, suppose you run Dudley's algorithm, okay, inside of this region here. How many facets do you need to do this approximation? Okay, how many facets are needed here? How many facets are needed here? Suppose I say, okay, I'm allowed to use 2 facets. In other words, I want a query time of 2 for my answer. Oh, here, 2 facets work, I'm done. Here, 2 facets work, I'm done. Here, 2 facets work, I'm done. So the algorithm is now going to be a little bit locally sensitive. Oh, but here, I need more facets. What do we do? Well, think of quad tree. You just split this guy again, and you ask the same question. Here, 2 facets work, I'm done. Here, actually, I don't even need any facets. And down here, though, maybe I can't do it with 2 facets. So I split again. And again, here, 1 facet, 2 facets. Okay, finally, I'm finished with the process. Okay, so a very simple hierarchical algorithm. You just run a quad tree decomposition. You ask how many facets are needed to approximate. And if I can't do it with the desired number of facets, then I go down to the next value. Again, remember, you might say, well, what is the value 2 here? This is the user. The user gets to decide how high the query time is going to be. So as the user makes the value, t lower and lower, I'm going to need more and more cells in my subdivision to make this work. If the user gives me a higher and higher value of t, then I can use fewer cells. So my time will go up or my space will go up in either form. But this is a very simple algorithm. We call this algorithm split and reduce because you keep splitting the space up and you sort of try to reduce the problem to an approximation on a smaller portion of the boundary. Okay, so what's the query time? Well, the query time can be seen to be this. First off, you have to do a search in this quad tree. The quad tree depth will never be more than log of 1 over epsilon. And the reason is because you start with 1. When you get down to cells of size epsilon, right, you can stop. So the number of levels is just going to be log of 1 over epsilon. And then when I get down to the leaf, right, I just have to look at all the t hyperplanes. So if the query point is inside of these 2 hyperplanes, then it's considered to be inside. If the query point is outside any one hyperplane, then I do nothing. Oh, but the storage, this is really hard to analyze. Okay, this is a mess. I mean, the idea is simple, but the analysis is kind of complicated. So I'm not going to give you the analysis. Okay, I'm going to cheat. I'm just going to tell you what our analysis produced for us. Now, the weird thing about the analysis is not a nice continuous function. The way we design the data structure is we actually analyze it in various phases. There's a first phase that gives you 1 point on this thing, and if we observe that the number of cells that are used for the approximation is too high, what we do is we run a second phase to try to improve things. And this point represents the space-time trade-off for the second phase. If we find the cost is still too high, we run a third phase, then a fourth phase, then a fifth phase, et cetera, et cetera. So in fact, the algorithm actually produces sort of these discrete points. Now, once you have a solution along at this point and when you have a solution at this point, there is some technique that allows you to sort of interpolate anywhere in between. But the interpolation is just going to be a straight line. It's just a linear interpolation. But you'll notice these points are actually not traveling in a straight line. Yes, so by the way, I think that the very first approximation that I described to you, the simple grid-based approximation, gives you this point right here. Okay? Maybe I'm wrong about that. I have to think. But the other ones give you basically these successive levels of improvement. So using the split-reduce algorithm, we can answer the polytope membership problems using this weird-looking formula. Like I said, it's hard to understand the formula, but I think it's easier to understand the curve. So you'll notice in the curve, remember what we're looking at here is the exponent in the epsilon factor. So I'm saying that essentially as the exponent in terms of x grows in one dimension, the query time is going to improve in the other dimension here. Okay. Yes. What about nearest neighbor searching? Remember at the very beginning I told you what we're going to do is we start with the nearest neighbor searching problem. We lift the points onto the paraboloid. We solve a problem of polytope approximation. Well, that should tell us something about the original approximate nearest neighbor searching problem. Well, if you go back and figure out from the results that we get, previous slide, if you look at these results that you get for polytope approximation and you plug them back into the AVD results, these were the old results that we had here, and these are the new results that you get. Okay? So in other words, remember that we proved that using an AVD-based approach, this is the best you can hope for, this is the best you can hope for, and this was the lower bound curve. The interesting thing was we find now that using this new approach, we get this intermediate curve here along the way. Okay? Now the problem, remember I told you at the beginning, the question is, what is the truth? Okay? God knows what the truth is, but I do not know what the truth is. This is a very hard problem. But this originally we thought was the truth because it was a very nice, linear function is a nice function. But we know this is not the best you can do. We now have this result down here. We have this lower bound down here, and the question is the lower bound correct, or is this curve the best you can possibly achieve? Now, I'm going to, for the sake of time here, I had a refined version to talk about. But let me just actually jump to the end of this stuff and show you what the results were here. Actually, there was not very much to say. I guess I was just going to say that there was a sort of a somewhat more sensitive approximation that can be used that comes up with a slightly better bound. So the crazy news was this, that we were able, by even using an even more careful analysis, we were able to come up with an even better result. So this was the result that I just showed you. This was the further improvement here. You kind of get this feeling like this is an asymptotic process. We keep getting closer and closer and closer to the lower bound. But, are we ever going to reach the lower bound? I don't know. But now I think we actually believe that the lower bound really may be the correct result. That maybe this is actually the value that we should be shooting for. So, by the way, if you're looking for a topic for a PhD dissertation, this may be hard. Okay, try to show that this actually is the result here. Again, I'm just going to show you the plots rather than going through the formulas. The formulas are rather messy here, and we wind up with this final result for approximate nearest neighbor searching here. So for nearest neighbor searching, this was the old curve that I showed you. Now, using this more refined method, we get this new curve. Okay, coming down through here, and then again, where is the truth? What is the actual what is the true complexity? If you really had access to the very best, way of sampling of doing polytope approximation, my conjecture would be it's probably close to this bound here, but it's hard to say what if that's really going to be the case or not. But it seems as though we're marching towards that result at the very end of the day. Okay, so let me wrap up. And remarkably, yes, I guess we're going to come back pretty much back onto time again, pretty close. So our results were the following. We presented improved lower bounds for approximate polytope membership queries. Okay. We used these, basically we were able to achieve space-time trade-offs for membership queries. We had a very simple algorithm. That's actually the nice thing about this, right? The algorithms, many times in computational geometry, when you go to high-dimensional spaces, if you think about algorithms based upon, I don't know, concepts like computing cuttings and things like that, I would not want to implement these algorithms. The algorithms here are actually relatively simple, at least in principle. The one thing you have to do, though, is you have to be able to solve the Polytope approximation problem as a black box. So I guess I have to solve that problem. But there's a kind of a simple, how would I describe this? There's an iterative algorithm that Clarkson gave that allows you to solve this problem, which is not very complicated. Oops, that was not yet where I want to go. So we were able to use this algorithm to actually give us, this area-sensitive polytope approximation. That was the refined bounds, and then we showed how to apply these things to approximate nearest neighbor searching. Let me mention two open problems here. So first off, the open problem is really, what is the truth? Okay, that is the hard problem, I think, here. So we've been working on this problem since, you'll notice my co-author is Sunil Arya. He started thinking about nearest neighbor searching as a graduate student in 1993, I think, or 92. Okay, maybe it was even earlier, 91. Okay, since 1991, he and I have been working on these problems. These results, as you see, they date from 2009, 2011. Okay, we are still thinking about these problems here. So, it seems as though there is more to be understood here. And every couple of years, we seem to kind of come up with an idea that'll get us closer. But we're kind of missing, my guess is that there's one sort of key idea that we need to find. And it is eluding us. But this is the nature of science, right? Somebody clever, like one of you guys, comes along and just says, hey, here's one cool idea. If you apply this idea, boom. Now you'll be matching our best result here. Let me mention another issue here. When I first started talking about nearest neighbor searching, remember I said this applies to any Minkowski metric. However, when you do lifting to the paraboloid, that only works in Euclidean metrics. The paraboloid, remember, it uses the squared Euclidean distance. If you have a Minkowski metric or other kind of a distance function, this technique does not work. You say, why doesn't it work? I don't have a good answer for that, okay? It seems to be an artifact. In other words, we converted nearest neighbor searching to polytope membership. To do that, we needed Euclidean distance. But maybe there's a direct solution to the problem that doesn't use this lifting technique. In other words, maybe there's a better way to analyze the AVD algorithm directly without using the lifting process. I don't know. Finally, let me mention one thing. I didn't mention this actually in the talk, but when you actually try to apply this stuff, you have to use a good algorithm for doing polytope, let's say applying Dudley. You can't just apply Dudley. You have to apply a kind of a sensitive algorithm that really does a good job of covering the polytope boundary efficiently. It has to be close to optimal. It would be great if we had an algorithm that is a constant factor from optimum, but it turns out this is a set cover problem that you're solving, a geometric set cover. The best algorithms for this kind of a geometric set cover problem have additional log factors in them. And this winds up giving us an extra log factor in all of our running times. I didn't show the log factors, but they're sitting there. It would be really good to get rid of these log factors. To do so, though, I need to come up with good algorithms for good geometric approximation problems, or geometric covering problems. In this case, the covering problem is, if I give you a polytope and I tell you that it can be covered by, optimally by a certain number of, a size. Suppose I do the following. I say, you can use, 10 times the value of epsilon. Maybe this, let's say using epsilon itself as the approximation value. You find, I need 1, 2, 3, 4, 5, 6, 7, 8, 8 facets to do it. Okay? And I tell you this. Suppose I gave you any constant bigger than epsilon, 10 times epsilon. Okay? Could you do this with, let's say, some constant times, 8 as the optimum solution? Right now, the best we have is, we can't do this with a constant. We can only do this with log n. But if you could figure out that if I allow you more error, a constant fact more error, could you come up with a constant factor, relative to the optimum? If you could solve that, you could get rid of all of our log factors in the construction, and this would be, I think, a very nice result. This would be a major result in this area of geometric covering. Okay, so now I can get to my final slide. So thank you all very much for your attention. And again, okay. And I'll be happy to answer. This has been the most technical talk that I've given this time here. So I don't know if it's been difficult, but if you have any questions, I'll be very happy to answer them. Yes.
After lifting the point, how did be inside or outside the polytope being nearest neighbor?
Yes. So how did you go from the inside or outside to nearest neighbor? So that's a good point, because you're right. Inside outside is just a yes or no question. Okay. Let me, again, because there were a lot of details that I was hiding, let me sort of explain that last little step. You really need more information than just inside, outside. You really have to know kind of what facet you're inside or outside of. So the way to think about it would be something like this. Let's say I have the points on the paraboloid. Okay. And again, here's my approximating polytope. Here's what we do, actually. Here's when the query point comes along. We don't actually just solve this directly. What we do instead is something like this. We run a binary search. First off, we find a point that is definitely on the inside. Okay? And then we start querying this guy. This guy says, oh, I'm on the outside. Then I search, I'm on the inside. Then again, I search, maybe I'm out. Now I'm in. At some point in time, you get very, very close to the right answer. And then you ask, which facet is making that cut there? Okay, that facet will be defined by a certain point P. That is going to be the point that you're going to use. So there's an extra log term here. We don't just use a single inside-outside query. We're sort of simulating a ray shooting query by a binary search process. Hey, welcome back. Okay. Any other questions that I can answer? Yes?
How did you map those sample points from a sphere to polytope?
Right. So what happens is, maybe if I'm understanding correctly, the sampling process goes something like this. So although you're sampling points, I remember now, this is the Dudley construction, right? So here's my convex body P. By the way, Dudley doesn't require that you have a polytope. It'll work for any convex body here. And then let's say I have this sphere that's on the outside. So these are my sample points, for example. Again, they're sampled uniformly. And then each one of these guys, oops, that's not a good picture. Each one of these guys computes its nearest neighbor. So by the way, a property of the nearest neighbor will be that if I look at the normal here, right, the nearest neighbor will always have the property that the supporting hyperplane will be normal to this point here. By the way, I didn't talk about how to actually do this. Let's just say that this can be done. Finding these closest points approximately can be done. So what happens now is whenever I compute the closest point, now I have a set of points on the boundary. And then what I do is for each of these points, I compute a supporting hyperplane for them. Okay? So I first go from these points on the sphere to these points on the boundary, and then for every boundary point, I compute a tangent plane there. And that's how I get the final. These are the guys that make up my final polytope here.
How much time does that take?
Yes, that is really a messy question to answer. I'll have to send you a copy of the paper, okay? I just wrote this stuff up in the last few months. It is not easy to describe. I have to use lots of techniques from other papers to get this do this efficiently. The trick is to make this very, very fast. What you have to do is you have to take this polytope and you have to reduce. You have to first off you have to make it nice and fat. So you have to transform it into a fat polytope. You have to prove that works. The second thing that you have to do is you have to reduce its complexity. So we first compute a crude approximation to it, and then we do this more refined approximation. So it's a multi-step process. So it's not easy for me to describe that procedure that we actually use. But yes, this still has to be done. So I said this was simple, but I kind of lied. This part of the processing, to get it to be really efficient, takes a long time. Let's say conceptually simple, But some of the implementation details here, the actual, finding these boundary points is a tricky thing. Yes?
Sorry, you know the nearest points in the polygon, on
Yes.
the polygon, does it mean that you have the formula of the polygon, so you have the hyperpoint?
Yes.
What's the approximation?
Oh, so the assumption that we make actually with respect to the polytope, we don't have a formula for the polytope. Actually, what we assume is that the polytope is given by perhaps an extremely large number of bounding hyperplanes, something like this, okay? And our objective is to come up with a smaller number of hyperplanes that approximates that. So what we actually will be using the original hyperplanes that were given, but we are simply going to be pruning these to a much smaller set. Yes. Any other questions? Yes. Yes.
What is the approximation ratio to that?
Approximation ratio. So the approximation value that I'm using is always epsilon. Is that what you're talking about? The approximation parameter? Epsilon refers to the following. So again, I assume that this guy has a diameter of 1, and the error that I'm allowed to make here is going to be an epsilon. Is this the ratio you're referring to, or is it something else? Yes. Yes, this is the ratio. So this is the ratio between the exact answer and the... Actually, so in this context, it's really an absolute error that we're making. Although you could kind of think of the ratio as being, the way we really think of it is the error that you're making relative to the diameter of the polytope. So if I give you a bigger polytope that's, let's say, 20 times bigger, then this error, right, is going to be 20 times larger as well. So you can kind of think of this as the error is going to be less than or equal to epsilon times the diameter of your entire polytope. So you can think of it if I think of the, I want to think of this as error divided by, if this is my ratio, then this is going to be less than or equal to epsilon. This is sort of what I have. Okay? Other questions? Okay, well, again, I'd like to thank you very much, but before I say goodbye, I have a gift for all of you. Okay? Actually, I have a number of gifts, but let me see if I can find my gifts here. And I thought I had pulled these out, put them somewhere. So as I left the University of Maryland, oh, maybe it's here. Yes, okay. As I left the University of Maryland, I went by the bookstore, and I got a whole bunch of these little University of Maryland. These are lanyards, what are called lanyards, right? Each one has a little keychain, and it says the University of Maryland on it. Now, I bought many different colors, and I bought many different styles. So, although I would like to give each one of you one personally, let me suggest that maybe I'll just leave them out up here, and as you're coming out, you can pick one up that you like. But in general, because I will not be around to talk tomorrow, which is the last day, I have to go back early because of my flight. I just want to take this opportunity to thank all of you for your attention. I want to say I have had a great time visiting Iran. I have had so much fun talking with meeting with all of you, and I've enjoyed stupendously all the time I've had here, even though I had to go deal with the traffic and everything else. So yes, again, finally, thank you all very much for your attention, and please, when you're coming out, please pick up one of these. I don't want to have to take them back with me. Again, thank you very much.